Hi everyone, in this video we're going to begin chapter 8 by going over some integration techniques. Now in this video we're going to be reviewing strategies for fitting an integrand into one of the basic integration rules. In this section we're not going to be covering any new integration techniques, but instead we're going to be reviewing some of the techniques that you have learned in a previous calculus course. Now if you did not cover any of this approaches or techniques, no worries, this video here is going to serve as an excellent starting point, or if you already happen to see these techniques, then it's going to serve as an excellent review. So let's go ahead and begin here. When presented with an integrand to evaluate, we're going to try to fit the form of the integral into a known formula. To do this, we consider the following techniques. Now the first technique that you might have used is to expand the numerator. Now the expansion here typically involves some foiling, so if we had the expression x squared plus 8 squared, we can go ahead and FOIL it out to get x to the 4th plus 16x squared plus 64. Now another technique here is to separate the numerator. So in the case, let's say that we had a fraction where we have x minus 3 divided by 1 plus x squared, well, we can go ahead and recognize that, okay, well, you have two terms in the numerator, so we can go ahead and split them up as x divided by 1 plus x squared minus 3 over 1 plus x squared. Now another technique that you may or may not have seen, although we did go over one example where we used it, the method of completing the square. And here is an example. We have 1 over the square root of 4x minus x squared. Now as it stands, it doesn't seem like we would be able to easily integrate this function. However, if we complete the square on the radicand, well, we have 1 over the square root of 4 minus x minus 2 squared. Now at this point you might be thinking, well, it doesn't look any simpler. However, if you remember your integration techniques involving the inverse trigonometric functions or sometimes the hyperbolic functions, then this integral is actually quite manageable. Now, another technique here is long division, also known as polynomial long division. Now here we have an example. X squared over 1 plus x squared, you can actually go ahead and rewrite it as 1 minus 1 over 1 plus x squared. If you're a little bit rusty with polynomial long division, no worries. We are going to be going over one example in this video, but I'll give you guys a hint. If you notice that the degree of the numerator is greater than or equal to the degree of the denominator, then that's a very good hint that polynomial long division might work. Not just a word, I'll write the word degree here. Alright, now another technique that can prove very useful is to add and subtract terms in the numerator. So let's say that we encounter the fraction 2x divided by x squared plus 6x plus 9. Well, in this case, what we can do here is essentially add a 0. Well, I'll call this one here a special 0, because if we add a 6 and then take away a 6, technically we're not adding anything, but this allows us to rewrite the fraction, the original fraction, 2x over x squared plus 6x plus 9 as 2x plus 6 over the denominator here minus 6 over the original denominator. Now when we rewrite it here, we might be able to simplify or integrate certain fractions. Now I'll just put here that technically we're adding a 0. Okay, now the other technique here, or the other techniques that we're going to be encountering, they could rely heavily on trig identities, and well, the next one here, the next technique is to use trig identities. Now I'll give you one here for example. Let's say that we encountered cosine squared of x. Now if we wanted to perform this integral, it'd be really hard. However, if you remember the half angle identities, you can go ahead and rewrite the cosine squared as 1 plus the cosine of 2x divided by 2. Now the last and final technique is to multiply by a convenient 1. Now this convenient 1 will vary by problem, but hey, one such example is a Pythagorean conjugate. Now this one here might be a throwback to your days taking trigonometry, but if we were to encounter the fraction 1 over 1 plus x squared, well, we could go ahead and multiply it by its conjugate, both top and bottom, to reduce the original fraction and rewrite it here as another expression. So it turns out here that 1 over 1 plus cosine of x is the same thing as the cosine squared of x minus the cosine of x times the cotangent of x. Okay, now we're going to be reviewing some of these techniques in this video, but I do want to point out that there are certain trig identities that I do expect you guys to memorize and know. Now the first one here is the Pythagorean identities. Now really the only one that you need to remember is just the Pythagorean identity. Sine squared of theta plus cosine squared of theta is equals to 1. The other two here, you can easily get them by taking the original Pythagorean identity and either dividing by a cosine squared or a sine squared. Because for example, if we took the sine squared plus cosine squared of theta and divide everything by, let's say, a cosine squared, well then you would see here that you end up with the following. Tangent squared theta plus 1 is equals to the secant squared of theta, which is essentially what we have here. Okay, and again, if you divide it by a sine squared, then you would end up with the third Pythagorean identity. Now, the other identities here are the double angle formulas. Now the sine case, it's very easy. If you have sine of 2 theta, then that's equals to 2 sine theta cosine theta. Now the cosines ones, they do have different forms, and depending on the problem, one may or may not be more convenient, but really the two that you should really have down here for the cosine is these two. The cosine of 2 theta is the same thing as 1 minus 2 sine squared theta, or the cosine of 2 theta is the same thing as 2 cosine squared theta minus 1. So these three double angles you should definitely have down. And the last one here is the half angle formulas. Now the half angle formulas, you might have seen them in a slightly different form when you took trigonometry course, but in this class, and later on really, we're going to be focusing on these forms of them. So we have here that sine squared of theta is 1 minus cosine of 2 theta divided by 2, and the cosine squared of theta is the same thing as 1 plus cosine of 2 theta divided by 2. Now these formulas here are fairly easy to memorize because you're noticing that the only thing that is different is the sign change in the cosine. Whenever you're dealing with a sine, you're subtracting a cosine of 2 theta, but whenever you're dealing with a cosine squared, well then you have a 1 plus a cosine of 2 theta. Alright, so these are the trig identities that you should have down. Okay, now with that said, let's take a look here at a couple of examples. Okay, so let's begin with the integral of 4x plus 1 divided by x squared plus 9. Now if I were to take a look at this problem, our go-to should always be a u substitution. So I'm going to go here and define u to be the x squared plus 9. Then this would give us a du equals to 2x dx. Now as it stands right now, I think this would be a good u substitution, but there is a little bit of a problem here though. My du has a 2x dx, which would work nicely with this for x. However, we have a plus 1 here that is throwing a wrench in our problem here. So what can we do? Well, I'll let you guys take a look at the above and see if you can come up with one approach that can help us. Alright, so if I scroll up here, so which one might work? I'm thinking that, hey, well maybe we could go ahead and separate the numerator. And that's exactly what I'll do. So I'll put here as a strategy, separate the numerator. Okay, so if we separate the numerator, we're going to have here the integral of 4x divided by x squared plus 9 plus the integral of 1 over x squared plus 9. And let's not forget here our dx. Okay, now, once we've separated the integrals, you get to see here that, hey, well, our u substitution is going to work great with this first integral. So let's go ahead and do the first integral. Now for this one here, I am going to be skipping a couple of steps because I trust that you have taken a look at the previous recordings and reviewed u substitution if you needed to. So now I'm just going to go ahead and do the following. So our du was 2x dx. Well, right now I have a 4x dx, but a 4 is the same thing as a 2 times 2x. So that means here then, the first integral could be rewritten as the integral of 1 du all over u, put the du here in blue, and well, there's a 2 that's a constant, so I'm going to go ahead and take it outside. Alright, so this is the first integral, which would give us 2 times, well, the integral of 1 over u du is simply the ln of u. I'll put here the ln of the absolute value of u. I'll add the plus c later once we figure out the other integral. Now speaking of the other integral, once that we have split it up here, we're now left with 1 over x squared plus 9 dx. Okay, so how can we do this integral? It doesn't look any easy. However, hopefully by now you're more familiar with some other formulas for integrals that we can use, and I'm thinking that this one here looks just exactly like the integral that would give you an arctan. Now I'm just going to write it here for the formulas. If we had the integral of 1 dx all over a squared plus x squared, then this is going to give us the arctan multiplied here by a 1 over a. I missed it here. So 1 over a times the arctan of x over a. Okay, so then this integral is going to be, well, let's see if we can identify the a. Well, the a is 3. So we should have here a 1 over 3 times the arctan of x over 3. And there we go. We've did the two integrals now, so I'm going to put everything together, and our final answer here is going to be equals to 2 times the ln of our u. Now in this case, our u was x squared plus 9, and I'll ask you this: could this ever be negative? Well, x squared plus 9 is never negative, so I'm not going to go ahead and include the absolute values, although if you wanted to include them, that's perfectly fine. So we're going to have here the 2 times the ln of x squared plus 9 plus the 1/3 arctan of x over 3, and let's not forget the plus c. And there we go. This gives us our final answer. So hopefully it wasn't too bad. Alright, so now let's take a look at the next problem. So for the next problem, we have the integral of 1 over 5 plus 3 times e to the x. Alright, so what can we do here? And again, we're going to go ahead and begin with our trusty u substitution. So I'm going to go ahead and let u equals to 5 plus 3 e to the x, which will give us a du of 3 e to the x dx. Now this one here, you might be thinking, well, there's a little bit of a problem here because, well, if our du is 3 times e to the x, well, I don't see anything like that in our numerator. Okay, so what can we do? Now again, if we go ahead and take a look at the strategies that we have here, well, it seems like we cannot really separate the numerator, we cannot expand it. It doesn't seem like it's a problem where we could complete the square. Long division, it's out of the window. Adding and subtracting terms in the numerator, I don't know, that might work. Trigonometric identities, well, it doesn't seem to be the case. And the last one here is to multiply by a convenient 1. Now for this one here, I think the strategy of multiplying by a convenient 1 may help. But what is that convenient 1? Well, one of the things that I noticed here is that since our du had an e to the x, well, we wanted to have something like an e to the x on the top. So maybe we could multiply by an e to the x? Maybe, but I don't think that's going to work too much, because if I multiply by an e to the x on the top, then that would mean that I would also have to multiply it in the denominator. I think that would just complicate things a little bit more. However, I don't think we're too far off with the idea of multiplying by an exponential. So what I'm going to do is the following. I'll take the integral of 1 over 5 plus 3 times e to the x dx, and I'm going to go ahead and multiply it not by an e to the x, but instead by an e to the negative x. Now, if we multiply it out here, we're going to get the integral of e to the negative x divided by 5e to the negative x times 3. Don't forget the dx here. Okay, now recall here that the only reason that we're getting a 3 here is because if we multiply an e to the negative x times an e to the x, well, that's just e to the 0, which is just a 1. Alright, now back to the integral that we're left with. We have the integral of e to the negative x divided by 5 times e to the negative x plus 3. Now, I think this integral is looking a lot nicer because, well, if we define the u to be now the denominator, the new one, 5e to the negative x plus 3, our du here, notice it's going to give us a negative 5e to the negative x, which is now what we have here. Okay, well, in this new form, a u substitution works just fine. So let's go ahead and finish it here. But before I do though, let me just clarify the strategy. In this case, the strategy was to multiply by a convenient 1. Okay, now I'm just going to move things a little bit over here and include the dx here. Okay, so now let's continue with our integral, now using the u substitution. And again, guys, I'm going to go ahead and skip a couple of steps here. Trust that you can follow them. We're going to have a negative 1/5 times the integral of 1 du all over u, which should give us then a negative 1/5 times the ln of the absolute value of u plus c. Now putting everything together then, we're going to have a negative 1/5 times the ln of Now our u was 5 times e to the negative x plus 3, which again, it cannot be negative, so I'll just write it here without absolute value. So it's going to be 5 e to the negative x plus 3 plus c. And there we go. We'd be done with this problem. And again, guys, there's no new integration techniques. It's just manipulating the integral to turn it into an integral that we can solve. And again, the hint for this one here was to recognize that since your du had an e to the 3x in the original u substitution, then it was probably worthwhile to have an exponential on the numerator. However, the exponential that worked out best was e to the negative x. Okay, so now let's take a look at one more problem here, and this is where we will be stopping part 1 of the video. Okay, so for our third integral, we have the integral of tangent squared of 2x dx. So what can we do? Well, we've reviewed a little bit about the half-angle identities, so maybe we could use the half-angle identities to rewrite the tangent, but I'm not sure if that's going to be the easiest thing to do. So what else can we do here? Well, for this one, I remember that the integral of secant squared is equals to a tangent of x. So can that help us? Well, as it stands, not really, because we have a tangent squared, not a secant squared. But can we maybe have a secant squared though? Well, you might recall here that we were just discussing the Pythagorean identities, and we saw here that there is indeed a relationship between tangent squared and secant squared, because you get to see here that tangent squared is really just the secant squared minus 1. So I'm going to go ahead and use the Pythagorean identity, and that will be the strategy. Alright, so using the Pythagorean identity, we have here that tangent squared of 2x is equals to the secant squared of 2x minus 1. Okay, so rewriting our integral then, we're going to have the integral of secant squared of 2x dx minus 1 dx. So let's go ahead and do those integrals. Now, since we have a secant squared here, I'll just go ahead and rewrite the formula for the integral of a secant squared. So we have the integral of secant squared of u is equals to the tangent of u plus c. So let's see, then the integral of secant squared of 2x is going to be equals to, now this one here, we do have a u. The u is 2x, so our u is 2 dx. So that means that we're going to have here a 1/2 times the tangent of 2x. Now just move it here. Now the integral of 1 dx, that's pretty straightforward. So our final answer then is going to be equals to 1/2 times the tangent of 2x minus x plus c. And there we go. This one here, not too bad. Alrighty guys, so this is where we're going to be stopping the part 1 of the video. We're going to be taking a look at more examples in part 2. See you there.